Good morning, everyone. So welcome to the Jessup last series, Jessup seminar series. This is the last one for this year, but definitely not the least. That we are very happy to have our star faculty from chemical engineering going to share with us the tutorial style kind of process control and etc. So before I introduce today's speaker, I would like to invite our dean, Dr. Farshad Futui, to say a few words, for this seminar series and what's our plan in the future. Farshad?
Thank you, Wei-Sung. Again, thank you also, Helen, and all of our speakers over the past month and a half, who were able to share some of their research that they are doing with our alumni, our university partners around the globe, as well as also our industry partners. And again, these are just a sample of some of our work that we are doing in the College of Engineering, and we are very proud of being able to present that to you. As I mentioned, about a year ago or so, about more than a year ago, we started a center in the College of Engineering called Global Engineering Education. We were able to present these series through that center with a gift from Jessup family. And we will hope to be continue doing that in the near future. I think this is one thing we learned during the COVID, that we can use the technology to reach out to our friends and partners globally. And some of the topics that we chose were some of the topics we felt like very important in today's Industry 4.0 manufacturing activities. So with that, I want to again thanks Helen, and I will want to pass the mic back to either Wei-Sung or Helen. I'm not sure who's going to take it from here on.
Oh, all right. Thank you, Farshad. Yeah, I wouldn't take it too long here because Helen going to be introduce those the research topic. But I would like to just briefly introduce Dr. Helen Durand, who is an assistant professor from chemical engineering. But very interesting thing is she is not just doing a traditional chemical engineering. As I mentioned several times during this speaker series, that today's the boundary between these disciplines is getting blurred. So you very easily see, for example, a professor from chemical, that might, she's using code here to show you how to do this, process control and to optimize them in this, although they might be starting with a chemical process, but this can be used for smart cities. Helen and I, we have some conversation how to apply this technology for the even supply chain, smart cities, and etc. So I think that was great, when we have this series, so that you can open eyes, when I normally chatting with some the junior students, they don't always stay with what you have started with. Some people might be starting with chemical engineering, and then you might be moving to some other relevant fields. So Dr. Durand has been at Wayne State. This, I believe, is the 4th year. Although I feel, she has been doing so many things, I feel like it's a quite impressive here. She got his bachelor degree, master's degree, PhD degree, all from UCLA, which I just visited last week. I was at the UCLA campus last week, so that was great. And today's talk, she will be talking about using this process control and apply it to the system engineering and do the optimization, etc. So without further ado, I will give the podium to Dr. Helen Durand.
Thank you very much, Wei-Sung. I'll go ahead and I'll start sharing my screen here. Oh, it says I'm not able to share it.
You are not?
It says host disabled participant screen sharing.
Oh, sorry, you should be the host. I will make you a host right now.
Thank you.
Okay, you are.
All right, here I go. Everyone can see okay?
Yes, perfect.
Great, thank you very much. Okay, so I'm, as Wei-Sung already said, I'm Helen Durand, assistant professor in the Department of Chemical Engineering and Materials Science here at Wayne State. And today what I'm going to be talking about is eventually advanced control. That's what we work on in my research group. But before I start talking about advanced control, I wanted to make this more of a tutorial style so that people who maybe don't have a background in control or even maybe chemical engineering still might be able to get a lot out of this talk. And so that's why it's called from classical control, which we'll discuss first, to advanced control. And so eventually we'll be looking at advanced control for systematic optimization of engineering system behavior. Before I start talking about what I really would like to talk about, which is control, I also really like talking about Wayne State. So I wanted to give a few cool things about Wayne State. I'll say that Wayne State is a really awesome place to be. It's very exciting here. We're in the middle of Midtown Detroit, and that's a really exciting area right now. There's a lot of revitalization going on in the city, and so Midtown is really nice. It's in a cultural area, but it's also not far from what's going on downtown, and it's a very exciting place to be, to go to school, to work. It's really great. And we have so many great colleagues. We're a very large school, so you can see we have so many engineering alumni and so many Wayne State alumni. So we're really making an impact in our community and in our world. We also have engineering programs for basically everyone. You can see here we have a huge range of engineering programs, all the way from biomedical, chemical and materials engineering, civil and environmental, computer science, electrical and computer engineering, industrial and systems engineering, mechanical engineering, engineering technology. You can see that's so many. So whatever floats your boat, we've probably got it. And this is our College of Engineering. It's really a cool building. And I also have a few other pictures of Detroit. These are ones I took. I just wanted to show that Detroit's really exciting. This is the GM Renaissance Center over actually next to Canada. And then this is what sunsets look like in Detroit. It's really pretty. This is actually a tree in fall at Wayne State. Look how amazing that is. It turned pink. I'm from Los Angeles, so for me, that's really amazing and beautiful to see a bright pink tree. And then also we have these really cool architectures all around. And then there's lots of fun things that happen in Detroit. This was at a Thanksgiving Day parade, and you can see this is actually downtown, and there's this really nice tree set up. And so Detroit's a really happening city, and chemical engineering is a really happening topic. So here I'll be talking a little bit about our department. And so one thing people might be wondering, if you're not a chemical engineer in the audience, is what is chemical engineering? So chemical engineering is concerned with the design, construction, operation, and optimization of processes that perform chemical reactions. And we have a few things that people might consider like our flagship industries, and that would be things maybe like oil refining and power generation. But chemical engineering is not limited to basically anything. You can work in pharmaceuticals, you can work in consulting, you can do so many different things. And I think it's testament to that. I can say when I got my bachelor's degree in chemical engineering, my job right out of college was to go and work as a materials engineer at the rocket engine company, Rocketdyne, that made the space shuttle main engine. And so I think that that is an example of how many diverse things chemical engineers can do. So I'm a really big proponent of chemical engineering. I think it gives people a very broad range of skills that allow them to go into all kinds of different disciplines and very exciting career paths and really make a difference and a change in our world. In our department, we have a lot of different research, and again, sort of showcases how broad chemical engineering is as a discipline. We have research in our own department in areas as diverse as battery technology, biomaterials and tissue engineering, catalysis, drug and gene delivery, molecular modeling, polymer and colloidal engineering, process optimization and control, and sustainable systems engineering. And here's the people who make that happen. I have 3 slides of our professors, so that just in case people want to look this up later, if you have interest in more of what we do in our department, this is sort of your introduction. So over here is the list of the names of professors, and then with some of their research areas. And if you even give a brief skim, you'll be able to see how diverse these areas are. And here's more of our faculty, again, with all kinds of different and diverse research areas. And then finally, here's the rest. So anyone who's interested in seeing more about any of us can just search Wayne State Chemical Engineering faculty in Google. You'll be able to pull up all of us, all of our research areas, and learn more about the exciting things that go on in chemical engineering. And so I think one thing that's really exciting in chemical engineering is control. And so I'm going to talk about that for a while now. So one thing people might wonder if they're not in the control field is, what is control? So control refers to manipulating physical systems automatically, essentially using a computer. And you might say, what kinds of physical systems would we like to do that with? Well, basically everything: airplanes, chemical plants, robots, cars. In general, control is a very important part of modern day engineering. And so the question would be, how do you do that? How do you actually manipulate a physical system using a computer? Well, the computer needs a little help from some other things. So there need to be sensors, and then the controller, which is the computer, also actuators. And then we're controlling this, what we call a process, which is our physical system. And I'll go into a little more depth on all of these. And so a sensor, you could think of that almost like your thermometer. It's something that's going to measure the condition of the process, and then it tells that condition to the controller. So it lets the controller know what's the state of our physical system right now. The controller then is like a computer. And so based on what the sensor tells it is the way the process is currently acting, the controller benchmarks and says, okay, is that what I want it to do? Do I want it to do something else? And then it tells the actuator how to manipulate the process in response to the current process state. The actuator then will change in a way that impacts the process. And so we can think about this control loop maybe in a nice way by thinking about a faucet and a sink. So let's say that we have a sink and that there's some level of water in our sink. So with our eyes, which are our sensor, we'll look and we'll say, what do I think about the level of water in that sink? Am I happy with it? Do I wish it was less? Do I wish it was more? And then our mind will act as the controller in that case to make the decision and to say like, oh, I wish the level in the sink is higher. And if we choose that, then we use our arm and we go and we manipulate the faucet. And so we'll say, okay, if I want to have more water in my sink, I'm going to turn on the faucet. And if I want to have less water, I'll turn off the faucet. And then that will impact the level of water in my sink. And so in general, we don't just have sinks that we're controlling. We can have processes across many disciplines. And that's the basics of how control loops work. And another one that's really common that people might think about is a thermostat in your house, where it measures temperature, and then based on temperature, it takes some action and says, am I happy with the current temperature? Do nothing. If I'm not happy, I either heat or I cool, and then that will impact the temperature in the room. So there's controllers in basically everything you do all day. So now that we have some basics of control, what is chemical process control? So that requires us to know what's a chemical process. So in general, chemical processes involve heating, cooling, separation, reaction, pressure change. You could think of that almost like cooking, that when you're cooking, you throw lots of ingredients together and you apply heat and things like that to try to facilitate changes in the materials that you're trying to cook. Similarly, in chemical engineering, we want to make changes in some original raw material to transform it into something that we would like to sell. But oftentimes in chemical engineering, we have really gigantic processes. So this is an example over here on the left of a really big refining operation. And so why do we want to do control of chemical processes automatically? Well, imagine operating this refinery like you do your stove. So when you're cooking, you kind of benchmark with your eye and you say, it looks hot enough and stuff, and you adjust some knobs and you hope you do a good job. But if we were just sort of hoping and having people stand by every valve at our process and adjust them by hand all day, we would never operate things like this efficiently. And so it's very important that we have good control algorithms for our chemical processes to operate both safely and profitably. So chemical processes transform lower value chemicals or materials into higher value chemicals and materials. And we have a lot of operating objectives when we do this. So we want to maintain safety when we're doing this. We need to meet our environmental regulations. So we need to keep our process under control so that we don't pollute too much. We need to meet product specifications. So we can't just sell any chemical that happens to come out of our process. Customers will only buy it if it meets certain requirements, like maybe a certain purity. And finally, we do need to make a profit. And so people are probably getting used to by now this idea that these feedback control loops are very helpful in achieving all of those goals. I did want to give a few more control engineering type terms here. So we have our process, and that we've defined, that's our physical system. But what we measure from that process is what we call in control engineering our output. And so for chemical engineering, that could be something like temperature, pressure, or concentration. we also have this thing called a set point. And the set point is the value we would like our output to take. And the error between the set point and the output is what the controller gets. And so based on that error, the controller can really tell how far off is my process right now from what I want it to be doing. And so based on that value of the error, the controller then computes something to tell the actuator about what input it should apply. And so input is the word for what the actuator does to change something like the output from the valve. So the output from the valve then could be the input to the process. And in addition to these inputs, which can change the process condition, disturbances can also change the process condition. And so disturbances are things that we don't have the direct ability to manipulate, but they're still changing with time. So they're still impacting the way that our process or system is evolving. You could think of a disturbance something like this. Imagine that you're storing your feedstock for a chemical reactor outside, and today is a hotter day than yesterday. So maybe the temperature in your tank is a little hotter in that case today than it was yesterday. So your actual feed to your process is a slightly different temperature today than it was yesterday. But you still need to get your reactor to give the same temperature that it did yesterday. So you have to counter this disturbance of the temperature of your feedstock. So in what I just said, there was a lot of discussion of the word change, that things are changing, controllers have to help with changes, they facilitate changes, disturbances make changes. And so because of all of this concept of change, which is what we call dynamics, we have to understand dynamics before we can control something. And so there are, in chemical engineering, many quantities in nature that are conserved, and these form the basis of the dynamic models that we make as chemical engineers. So things that are conserved are things like mass, energy, and momentum. Showcase this with a really simple example. Here, I demonstrate what it would look like to do a mass balance for a tank. So you want to say the mass in that tank is going to be conserved, meaning that the accumulation of mass in that tank equals the amount of mass coming in minus the amount of mass going out, plus the generation of mass in my tank. So overall, I can write the mass in the tank as equal to the volume of the tank times the density of the fluid in the tank. And the volume can be, if we have a cylindrical tank, the cross-sectional area A times the height or the level of the fluid in the tank. We can then look at the accumulation as the change in the mass over time. We can say the mass into this tank is the volumetric flow rate coming in times the density of the fluid. The mass out of the tank is the volumetric flow rate of the fluid going out times the density of the fluid. And the generation of mass in the tank is none. We're not having any reactions here to change like a species mass or anything like that. We're just going to assume no reaction. We're looking at one species all the time and no change in mass. And then here in the end, we get this mass balance for our tank. And as you can see, this is a differential equation. So this expresses the dynamics of our tank. So it shows how the level is going to change in time when things like the flow rate into my tank and the volumetric flow rate out of my tank become different. And so this is the first point where we're going to look at some simulations to help demonstrate this concept. And the simulation that we're going to look at is one where we have the level in our tank. There's an initial value of the level, and we know that if the flow rate into this tank and the flow rate out of this tank are the same, the level in this tank won't change from our own intuition. But if the flow rate into our tank becomes greater than the flow rate out of the tank, then the level of fluid in this tank is going to start rising. And so that's what we're going to see in this simulation, is that the flow rate in is greater than the flow rate out, and so the level is just going to increase. And so the way that everyone can run this simulation, we're going to look at it in Jupyter notebooks. I guess I should check. Can people still, can people get to the note in the chat still, or do I need to repost it? I don't know always how the Zoom chat works, if people can access it after they join or if I should repost. Maybe I will repost just to be sure. So I'm going to put a file here, and this file is just a Word document. So the reason I'm posting that, you don't really have to look at it. I'm not going to go through the codes line by line. I'm going to actually show a dynamic simulation that shows the level changing with time, kind of in real time. But if people are interested in seeing like what code am I running, then that just gives you the opportunity. But you do not have to do anything with that code if you don't want to. No, not necessary. So let's look at our first simulation here. And so as I mentioned, I'm going to run this in what we call Jupyter Notebooks. So I'm just going to run it in this browser one. Anyone can actually find the same thing. You just type Jupyter Notebooks in Google, and you'll be able to also open them and run this same code. And for reference, this is the website to go to, jupyter.org/try. And that's where you'll be able to say that you want to try it in the browser. And so I'm going to post this here. I'm going to press run. And so here's my dynamic simulation. So people can see that we have the level in the tank here and time. You can see the level in this tank is increasing with time because of what I mentioned, that the flow rate into this tank is greater than the flow rate out. And so this is showing that aspect. And so something that's also important with dynamics is the rate at which things are changing. So here you could kind of see, okay, over about 0.1 seconds, the level in this tank increased by about 0.03 meters. So that gives you a sense of the speed with which things take place in this system. And that's important for understanding things like, how do you have to set up your safety strategies? How much time do you have from when something starts changing before something catastrophic would occur? It just gives you a benchmark for like, how fast is this thing? It's also helpful for when you do control at knowing how fast your process is going to react to the things that you manipulate in response to other changes. So let me first just take a benchmark here. Anyone have any questions, or people are okay? All right. Well, I'll keep on pressing forward then. So that's the basics of dynamics and why we care about dynamics and control. So now let's go back to the control loop and start asking a new question. What algorithm should this controller be using to determine what input to apply to the process? And so a very common one in chemical engineering is proportional integral derivative, or PID control. This is a case where the input or control action, U, is equal to some function of the error. So that error, as we stated before, is the difference between the set point for our output and the measured value of our output. And this is called PID, or proportional integral derivative control, because this is the control law. And it has this term with a proportionality constant times the error, a term that's the integral of the error, and a term that is the derivative of the error. And these scalar values here, Kc, tau I, and tau d, can be picked or tuned by a control engineer to try to achieve a good process response. So how would you actually implement that in a code? Well, let's talk about a PI controller. So say I remove the derivative part. This would be what a PI controller then looks like. And so in order to handle this part here, that's the integral of the error, we'll handle it with numerical integration. So here I add this dynamic state to my control law, and this is representative of the integral of the error. And if I take its derivative, I get back the integrand, and so that's just the error. And so by using this set of two equations here, I can simulate my PI controller. And so now we're going to get to see what that same level simulation we looked at earlier looks like if I add a PI controller to it. So what we had before again is the level in the tank would remain constant if the flow rate in was equal to the flow rate out. If we take no action when the flow rate in is greater than the flow rate out, the level in the tank is increasing. But now we're going to use our controller to counter that. What we're going to do is we're going to put a PI controller that's going to adjust the flow rate out to try to keep the level at the 4 meter mark, even when the flow rate in changes. And so those who are interested in looking at your code, this will be the second example. I'm gonna put this one now in the Jupyter notebook. And we'll also watch a dynamic simulation here. So in this case, I'm going to press run, and now we're looking at the level once more. So here we can see the level is gradually increasing as it did before when we had no control. But here we see a slightly different effect. So in the past, it just kept increasing, 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 almost in a linear looking way. But here we see it's leveling off. So the level in the tank is starting to reach a new constant value because of the action of the controller that allowed it to stop just continuously increasing and help prevent it from continuing to increase. So we can see that flattening off right here. And then we can see down here what the controller did. So here we can see that the controller changed the value of the flow rate out until it increased to approximately the same value as the flow rate in. And by doing that, it was able to prevent the level in the tank from continuing to increase indefinitely. However, we might say, well, okay, that's great. It prevented the level in the tank from continuing to increase. But what if I actually really wanted it to be exactly 4 meters? Can I do any better than just preventing it from continuing to increase? Can I actually bring the level back down after it's initially disrupted and brought off of the 4 meters and brought to a higher level? Well, this comes to that question of controller tuning. So here I have my KC and my tau I in my code. Those are ones that I had selected. Let me choose a new one. Now, that looked like I kind of randomly updated that. That was not random. I've run this simulation earlier and I already tuned the controller myself, which is why I chose that. But here we can see a different behavior than before. We see that the level is increasing like it was initially, but then after that, it's starting to decrease back down toward 4. And so that's a different behavior than what we observed previously. So we can see that by changing my controller tuning, I actually am able to get a different, what we call closed loop response. So a different response of the system when the controller is operating it. And so that gives a sense of how control sort of works and how dynamics play out in different ways, depending on the different control laws you choose and all of those types of important things. Anyone have any questions so far? No? Okay, great. So with that, we can start saying, okay, so are we good? Like that looks like I can just adjust these parameters, KC, tau I, tau D, and be kind of happy. I can get different responses. Am I done? Is there any more to do in control? And so, well, we can start saying, does this do everything I really want? And the answer is, it can be a little challenging to make it do everything you want. There's KC, tau I, and tau D here are these tuning parameters. And as you could see just now, I was able to kind of run the process earlier and find some values that did different behavior. But if you really want to choose optimal ones, you have to have a lot of experience, or you have to have maybe a simulation to try to help you figure out which ones give you the best response. And so it's not necessarily super straightforward to just say, what are the optimal values of KC, tau I, and tau D? Also, this type of control law does not account for some of the complexities in process behavior. Like this is the control law that you have when it's PID. And the only flexibility you have is to change KC, tau I, and tau D and maybe knock off some of these terms, say, okay, P only or PI only. But you don't have the ability to completely change your control law to try to get a completely different closed loop response. Let me check the question in the chat really briefly. Okay, thank you for your question, Alan. Does the derivative element increase response time? That's a very good question. So the derivative element, does it actually increase it? I believe that it might have a way of, I think I would have to go back and do a proof to myself to make sure what the response would be. In the end, the way that this works would, you would put it on your process and then you would see what happens. So for certain types of processes, you can probably demonstrate like, okay, the derivative of the error has this type of characteristic that for a certain class of systems, like maybe some type of linear system, you can demonstrate ways that the having the derivative of the error is going to impact your process. But then in general, because we can have so many different types of processes and they're not only linear or only of one form, I think that you can try and see what happens. But yeah. So I see there might be another question. Okay. Yeah, thank you, Alan. Yeah, there definitely are. It doesn't always have to be completely iterative. There definitely, for certain classes of systems, are proofs of what can actually happen. But then, but I think I would be really hesitant to give like always this happens, because a lot of times in chemical engineering, we're talking about nonlinear processes, and so then it would be hard to make potentially a general proof for like every nonlinear system of how that would impact it, even though I think you should be able to linearize your dynamics and then look at the corresponding linearization and say like generally it might act like in a certain way according to approximately how the linearization behaves. But because of those sort of drawbacks of the proportional integral derivative control law, we want to think about what can we do to do a better job. And so in the idea of more advanced process control, we start saying, what if I don't want to be restricted just to the PID control type framework? And I want to instead use a dynamic process model to help me choose the dynamics that I ultimately want from my closed loop system, and then try to force myself to get them. So when I know my dynamic model, either from first principles or from identifying it from process data, then what I'm able to do is to start saying, okay, this is how my process does behave. Here's my target behavior. What control action is the bridge between those two things to try to get me exactly what I want? And so you could see that by looking at this example. So what does it mean to use a process model in a control design? So here we have that the derivative of the state is equal to x squared plus u. So this is super simple. This doesn't represent necessarily anything physical. But here we have u is equal to negative x squared minus x. Let's say I choose that. Well, in that case, I cancel out this x squared here, and I'm left with minus x. So the closed loop dynamics, meaning the dynamics under the controller, are now x dot equals negative x. So in this case, you can see what I did, that I said, okay, here are my dynamics. What I want them to be is this. What u is the bridge between going from here to here? And we see that this u gets me here. And so that gives me a lot more flexibility to specify responses than I could get with just the traditional PID type control law. And you might say, well, why are we looking at these nonlinear processes now? Well, because in chemical engineering, a lot of times we do have nonlinear processes. And you can see this by even just considering one of the very most simple chemical engineering processes, which is a continuous stirred tank reactor, or a CSTR. And so in this case, we have just a continuously stirred tank. We have a concentration of the feedstock, concentration of our reactant A coming in at a temperature T naught. We have a flow rate out of this at a concentration Ca and temperature T. And then we have this heater with heat rate Q. And so this is just all we have. It's that simple, one reactor, like one stream in, one stream out, and a heater. But in this case, already we have a nonlinear model. And so you can see what we get from our mass and energy balances down here. And where the nonlinearities come in is they come in through these exponentials of the temperature and the constant multiplied by the concentration, which are our states, because they're the things that are changing with time. And you might say, well, why are those there? That's because of our reaction rate laws. So given that in chemical engineering, we're often doing reaction, if reactions are causing nonlinearities, in general, in chemical engineering, we're going to get nonlinear ordinary differential equations. And so because of that, I want to make some notation that I'll use to say, okay, this is a system of nonlinear ordinary differential equations. And so let me define that notation. X here means the vector of the process state, which here will be our temperature and our concentration, because that's what's changing over time. And x dot, or dx dt, is the time derivative of the state. U is equal to our vector of our inputs. So here, let's say that my input is my heat rate, that I'm going to manipulate that with my controller. Now U is going to be the heat rate, and W is my disturbance. So here I might say, okay, pretend that I have a time varying concentration of my reactant. Maybe I have some type of feedstock that's not 100% consistent in the exact composition. And so then that's my disturbance. And so This is the notation then that we'll use to say we have a system of nonlinear ordinary differential equations. This says that the time derivative of our states is equal to some nonlinear function of our states, our inputs, and our disturbances. And so what we're really interested in is doing control design for systems of this type. And so I was mentioning that there are some ways that maybe we can cancel out nonlinearities. For example, like what we did in the case where we had u equals negative x squared minus x to in the end get something like x dot equals negative x. That's one way of trying to design controllers. And then the thing that is really exciting to talk about is model predictive control. And so that's coming up here. But before we can really understand a lot of things about control for nonlinear systems, we have to understand a really important concept for those called stability. So stability is whether or not if you start close to an equilibrium point of your system, meaning a point where if you start there that you stay there. So if you start close to this point, do you eventually stay near that point and or go even closer to that point and eventually reach it? Or do you move away? And so you can think about that with a pendulum. So say that you have a pendulum and you're able to like 100% perfectly balance it so that it's straight up. This is an unstable equilibrium for that system because as soon as you tip it in either direction, even the smallest amount, it's going to stop being straight up, not go back to being straight up, and instead go to being straight down. And if we start in the straight down position, we can say that that's a stable equilibrium. Because if we perturb ourselves slightly and we kick it a little bit off the straight down position, then it eventually goes back to that. And so even in our intuition, we can understand this concept of an equilibrium being stable or unstable. And so for a pendulum with friction, we can actually write some differential equations that describe the angle between the how the angle between the pendulum and the vertical axis, which is this theta, and its time derivative are changing over time. And this then will have different equilibria that say, okay, it's not changing over time anymore at positions where it can stay there. And then we can actually look at this concept of the stability of the equilibrium at the bottom here by saying, okay, well, the energy of the system is equal to the sum of the kinetic and the potential energies. And when I have friction, the energy is going to decrease over time. And when I get to the position where it's straight down, it has zero energy. And so in this case, it's really interesting to think about that concept says that we were thinking about stability of our equilibrium by looking at the non-increase of another function that was energy. And so that is sort of the way that you can start thinking toward the concept that we use in control of Lyapunov stability. So in Lyapunov stability, we do something very similar to what was just described. We have to define a function. That function is positive, except at our origin or our equilibrium point where that function should evaluate to zero. And this is then called a Lyapunov function, which we often denote by V. And so say that this is one of our system trajectories. So say that we start our system here, and this is the way that it evolves. It goes along this blue line, and that reflects how x1 and x2 are changing over time. So each point on this plot is a different combination of x1 and x2 at different time points. So if this is the way our system is evolving, and if we were to compute the Lyapunov function along this trajectory and it was always decreasing, then even if we didn't know how this trajectory looks and we didn't plot it, we would know that, oh, we must be approaching the origin. And the way you can tell that is that V is positive when we're not at the origin, and it's also increasing. And if we cause it to decrease, 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 then that means we must be heading toward the origin, because the origin is the only place where this function is zero. That function is increasing as it goes away from zero. And so therefore, if we eventually keep decreasing it, we must eventually cause it to equal zero, meaning we must eventually hit the origin. And so we can use these Lyapunov functions, these alternative functions, to represent to us whether or not a system is stable, or a system's equilibrium is stable or unstable, meaning when we start our system close by, it eventually evolves to reach the equilibrium, or it doesn't. If it goes away, then that would be the case that it is not stable. But we use Lyapunov stability theory to help us understand whether or not an equilibrium point is stable. And so this is what we call here a Lyapunov level set. If it's the set of all points where the value of the Lyapunov function is equal to a certain value. So here, this set of red points is where the Lyapunov function evaluates to a given value row. And then, so this set would be what we call forward invariant, the set of all the points inside of this, because we're not able to leave this set. So it's invariant. Once you're in it, you're in it. We can only move toward the origin in this set, but we can't move away. And so that's the concept of stability. And so we can also see the way that the Lyapunov function is decreasing in another simple example. So here's what we're going to look at. X dot equals x squared plus u, and u is equal to negative x squared minus x. Same one as earlier. So the closed loop system dynamics are x dot equals negative x. So here we can talk about what if we chose a Lyapunov function. Again, it's positive and it's increasing away from 0, but it's 0 at 0. Something like this, v equals x squared. So if we take its time derivative, we, with the chain rule, would say that's 2x times x dot, which is 2x times x squared plus u. And then we can plug in our value of u here, which was negative x squared minus x. And eventually we find that v dot is negative 2x squared. That's less than 0 no matter what value of x we choose, because if x is negative, x squared is still a positive number. And if x squared is positive, it's a positive number. So a negative times a positive number is always going to be negative. And so we can actually watch in our final Jupyter notebook, the other ones are in the Google Colab, we can watch the value of our Lyapunov function decreasing over time for this example system. So here we go. So here is our value of our Lyapunov function v, and we can see that for the system, it's only decreasing with time. And that's because we are controlling the process with that controller that causes v to decrease. And here we can see how the input u is changing over time. And here we can also see the value of x, that it's decreasing over time. So it's approaching the origin over time. I mean, not in any fast way here. I mean, at least not over 0.1 seconds, it's not there yet, but we can see it having a decrease. And so there we go. So that's basically our intro to control so far. Next is our starting to move into model predictive control. Are there any other questions before I start moving into model predictive control? No? Okay, well, feel free to ask at any point. So then we can say, okay, great. I feel like I did better than before. So already my PID controller started off like it was. I was able to control a system. I could change my tuning parameters. I saw what that looked like, that I could achieve different types of behavior by changing my tuning parameters. Then we said, well, what if I want to really spec out my behavior? And I want to not just have this one PID control law and just try to tune within it. What if I want to spec out the behavior a little more? And then we said, well, great. If you understand stability of nonlinear systems and you understand how they operate and their dynamics, then now you can start specking out things in new ways and being able to get controllers that cause certain behavior to happen, that are stabilizing and drive you toward certain equilibria, etc. So what could be better than that? So then that's where we get optimization-based control. We want to find not just a stabilizing control action in this case, so not just one that will cause our Lyapunov function to decrease over time so that we can eventually know that our controller is causing us to approach an equilibrium that we might want to operate at, but also we should be finding a controller that is the best with respect to some metric that's also stabilizing. So it's not obvious how to just find the best controller. Do I just think of that off the top of my head and I hope I code it? Well, instead we use optimization, and we have to solve an optimization problem to help us find the answer to this. So now I'm going to really briefly go off of control and give a little background on numerical optimization so that people can feel like they have some sense of what I'm talking about here. So here's two textbooks I really like, Numerical Optimization and Convex Optimization. This Convex one is actually available online. The author has posted it on their website. And so here's the link if people are interested in this book. So the main concept that we need to ask for numerical optimization is, how do you get a computer to find the answer to a constrained optimization problem? So here's an example of a constrained optimization problem. And this one is really simple, but it demonstrates the idea. So I want to find the value of x that will minimize the function x squared such that I have this constraint. 1 is less than or equal to x is less than or equal to 2. Now for this example, you can even eyeball it. You can say, okay, so x squared, when x has to be between 1 and 2, okay, definitely the value of x that will minimize this is 1, because when I can only restrict myself between 1 and 2, that's like the lowest I can get this value x squared. In general, we don't have things that are that simple. So we do need to make some definitions of different parts of an optimization problem so that we can start talking about them when we have a more complex case. So components of an optimization problem, we have our objective function x squared. This is a metric that represents our system performance. So I can replace this with any different type of objective function I want, any different metric, but it should always represent our system performance. Then we have what we call decision variables. Here, that's this x. It's the thing that the optimization problem is going to decide. So it's the variables you want to find the values of to optimize your objective function while you meet your constraints. And then your constraints here, for example, is 1 less than or equal to x less than or equal to 2. In general, you can have equality and inequality constraints. You can have many constraints. And so that is the way that we do this modeling, meaning that we determine our objective, our variables, and our constraints for a situation where optimization can be useful, so that then we can translate our physical situation into an optimization problem, solve it, and get back some useful data so that we can do engineering. And so how does a computer actually do numerical optimization? Well, algorithms are needed, and different algorithms are best suited for different problems. An engineer has to choose the right algorithm for their task. So non-ideal algorithms might mean your problem is solved slowly or that you don't get any solution. And the computer knows whether or not the optimization problem is solved because there's a termination criterion that says when this condition is met, stop the algorithm. And there's a really robust optimization theory that clarifies a lot of things, like when do we know that the solution is optimal and things like this. So let's talk about the structure of an optimization problem. So we say that we optimize within our feasible set. So here's a new optimization problem. And this one gives us our objective function, which here you can see if you set this equal to a constant, it's the equation of a circle. So values of the objective function that give a constant number are going to be circles. So for example, all of these points on this circle, they have the same value of the objective function, even though they have different values of x1 and x2. And so these are the contours of our objective function f, where meaning our objective function is a constant. And then we have these two constraints here. So this constraint, we can look at this one first and say, okay, that would be like this region of my state space. It's the values where x1 squared minus x2 is less than or equal to 0. And then I can say the second constraint here is this part of our state space here where x1 plus x2 is less than or equal to 2. So then now we have to combine those two because both of these constraints have to hold at once in our optimization problem. So it has to be true that any point that we choose as being optimal has to meet both this constraint and this constraint. So that happens in the region where these two constraints are both met, which is this part. You can kind of see if you combine these two, you get this region, which is where they both hold true. And then this is our feasible region right here with our nice star. And then so our optimal solution is going to be the value of this objective function that is as small as possible in the feasible region. So we're restricted to this feasible region here, and then we can put our contours of our objective function here. And we say, okay, here is like this corner right here of my feasible region, which is able to jet as far as possible toward my, my lowest contour of my objective function. And so we say, okay, here's my optimal solution. It's right there. Now, in general, we have much larger problems that we can't visualize in optimization, and that's why we get the computers to help us out. In optimization, the basic way algorithms work is you start with some guess of the decision variables, and then they make better and better guesses over time until you find a solution to the optimization problem. And algorithms are different in how the guesses are updated. So here we're going to look at a small example optimization problem. This time we're going to switch from Jupyter Notebooks to Google Colab. And so in this case, we have this optimization problem. So we have 3 decision variables here. We want to minimize this objective function, and we have some constraints. So we have bounds on our 3 decision variables. So each of our decision variables can only be in a certain range. So x1 is between -5 and 5, x2 is between 0 and 10, and x3 is between -1 and 2. And then we have these 2 constraints here. These are equality constraints, and these say that x1, x2, and x3 have to be related to each other in some very specific ways. So I also want to highlight these what I'm presenting here. The problem I'm presenting is actually inspired by a problem that's in this website here at the bottom. And this website is really cool for anyone who's very interested in optimization. This is a class on optimization from Notre Dame in chemical engineering. And if you look at some of these different resources, you'll actually be able to find a lot of things about different optimization problems, and it will teach a lot of things about optimization for people who are interested. And this is from Alex Dowling in chemical engineering there. So let's look at our Google Colab. So the Google Colab file has several parts. So it needs to get some different software here. So we're trying to get an optimization solver to run in Google Colab. And so there's something called IDEAS. And so that's something that we're going to install here because it allows us to use IPOpt with optimization. We're not going to use a lot of the IDEAS functionality, but this is sort of a nice platform for enabling us to write some pretty easier codes for running the optimization problem in the browser here and having additional functionalities if people want to use it, but I won't really talk about those. Okay, and then here we're going to use Piomo, which got imported as part of this code up here. So Piomo is going to be used related to finding the setting up and modeling and our optimization problem. So here we say we're going to make our model for our optimization problem, and it says here's the decision variables x1, x2, and x3. For each of these, we're going to give them an initial guess, so initialize, and then we give them our bounds. So that's what we also said on our slides. We said that there's also these bounds. We also have to set our objective function. So here you can see the objective function is being written as the relationship that we had before, which is a function of our decision variables, x1, x2, and x3. We're going to minimize it. And then we wrote our two constraints here, which are these equality constraints. So the first one says that this function is equal to 15, and the second one it's equal to 10. And so we can run this, and then it comes back and sort of shows us, okay, like, so your first decision variable x1, for example, its initial guess value is 1, the lower bound on it is -5, and the upper bound is 5. And you can see here it writes out the objective function and it writes out the constraints. So that shows us that we set this up right. Then here I'm going to solve with IPOpt. So IPOpt is an open source optimization solver. It's really nice. We use it a lot in my group. And so I think if people are interested in doing optimization, IPOpt is a great place to go. And so here it says it found the optimal solution. And so we can print what did it find. And so here's what it found. It found that the first decision variable is about 2.2, the second one's about 4.2, and the last one's about -1. And then we're going to run this plot here, or this we're going to run a plot here. And what this plot does is it helps visualize how optimization works. If I run this code, it is going to show me that my optimal point here, the one that my solver returned for me, is the one that has, as you can see here, the lowest value of the objective function. And that's exactly what I was looking for. And if you are interested in how does that code work, one thing that's interesting to note is that the two equality constraints here, which are part of what's important for defining the feasible region, can actually be written as a system of linear equations. And so you can see here that if you fix the value of x3, then you can find the x1 and the x2 that satisfy those constraints. So then what you can do is you can say, okay, x3 within its bounds, let me choose different values of x3, solve these equations, find x1 and x2, and if they're in their bounds, then I can compute the value of the objective function for that combination of x1, x2, and x3, and then see how good it is. And so that's actually exactly what happened in this code, is that that I have here that the x3 is discretized in its range, and then that we solve the system of linear equations, that then we say, okay, if I'm in the right bounds for my decision variables, then I'm going to store the value of the objective function and also store the value of x3, and then I'm going to make this plot with the values that work and see that my optimal solution was the one with the lowest value of the objective function, which is what I wanted because I was trying to minimize it. And so again, that's inspired by the code that's here. That was another example very similar to this one that did the same thing. And this one is just a slight modification on that. But this example was from Notre Dame, is the one that inspired this code. And basically I followed along with that. because it's a very nice problem for demonstrating properties of optimization. So any questions before we keep going to model predictive control and move back to control from optimization? Don't see any question in the chat or hear any, but feel free to interrupt at any time. Okay, so now we have, with that, we can start talking about optimization-based control, because now we have some basic understanding of optimization. So where did we leave off with control? So a standard for chemical process control has been classical control laws like proportional integral derivative control. Most chemical processes are nonlinear. So model-based control allows us to account for nonlinearities to achieve more desired responses from a system. That may be more preferable than just trying to tune our control law to get good things to happen. This requires that we have an understanding of how nonlinear systems behave, their dynamics, things like Lyapunov stability, which are important for understanding aspects of the dynamics of systems. And so then we said, okay, how am I going to do better than these like model-based control laws that we talked about previously? So we can do better in a systematic way. We don't prefer to just try out lots of control laws and say which one of these was the best. Instead, we want the computer to help tell us what's the best way to operate this process. The way we can do that is by making a controller that is actually itself an optimization problem. So the controller will solve for the best inputs to apply to the process that respect constraints. And so this is sort of the mathematical representation of where we're at right now. We have our nonlinear process model. And we said, okay, even if we have a control law here denoted h of x that can cause v dot to be negative, that's not necessarily enough because we didn't yet account for performance considerations and constraints explicitly in our control design to allow us to do better than what we talked about before. So this is where model predictive control comes in. So right now I have several slides that are just like back to back. Here's the basics of MPC. MPC is has like a lot of layers to it of things to understand. So I'm going to just sort of go through the high level overview of like, here's all the components of MPC, but then we'll break it down a little more through the context of a process example or a small simulation example. And I think that that will help a lot of these things to come together a little better. So MPC, as is written here, is actually an optimization problem. So since we've learned about optimization, this probably looks pretty familiar to everyone. We're going to minimize some objective function. Our decision variables here are the inputs. So we're solving for the inputs that are optimal. And then we have our constraints here. And for MPC, a lot of times in industry, the way that it's implemented is with a quadratic tracking stage cost. And this might be something like x squared plus u squared, for example, if you have a single state and a single input. And the optimization of MPC is solved every delta time units, where delta is what we call a sampling period. So we say it's solved at every TK. So that would be like T0 is the first one, T1 is the second one, et cetera, et cetera. And so the solution of the MPC is a piecewise constant input trajectory with n pieces, where n is what we call a prediction horizon, and each piece is held constant for a period delta. So the idea here is demonstrated via this red trajectory. So we can see here between TK and TK plus 1, my input is held at a constant value. So it's piecewise constant. At TK plus 1, I'm allowed to change it again. And I keep making it change every delta time units, which is the length of a sampling period, until I get to the end of the prediction horizon. And so when we solve this MPC optimization problem, it's just like we wanted to do before. We want to find the values of u that make our objective function as small as possible. But we do have a little bit of a different thing than before. Here we actually have a dynamic model listed as one of our constraints. We'll see how to play that in a few minutes, but the idea is that the predictions of x into the future that occur in both our objective function and our constraints have to come from this dynamic model. We have an initial condition set equal to our state measurement, and we have these state and input constraints. And so because in chemical engineering, we often have these nonlinear models, so typically you would have to use some type of nonlinear programming, which is optimization for a nonlinear problem to deal with this. And an important issue that we're also going to see in a minute is this question of feasibility. So that means, does there exist any u that can cause all of these constraints to be satisfied at once? And so you actually have to design your controllers carefully, because if you don't, you'll end up with situations where there is no control action that can satisfy your constraints. And that would be a problem, especially if your constraints were based on safety. And we implement MPC in what's called a receding horizon fashion. So this means that even though we're going to calculate an input trajectory that goes across the entire prediction horizon, we're only going to apply this first piece from TK to TK plus 1. And so you'd say, that seems crazy. Why am I solving for things that I'm not going to ever implement on the system? Well, the reason is that a real system doesn't actually behave according to your process model. It's a little bit off. You have what we call plant model mismatch, where your actual system, which we call this plant, and the model of your system are not exactly the same, because we just don't fully understand every detail of physics, or we can't measure every single thing that's actually happening all the time to be able to make our models perfect. And so if we just apply the control actions that we calculated at one time for a long time, because of this mismatch, those might not actually be the best control actions to apply to the system. So instead, what we do is we predict what should be the best control actions, but then we only apply one of them. And at the next time we measure again and we say, okay, where's the process at now? And then we update the control actions that we're going to apply, so that we're always trying to apply the best one that we can given our current measurements. And so we're going to look at a small example to demonstrate a lot of these concepts. So in this case, I'm going to just choose this nonlinear system, 2x squared plus x plus u. Here's, again, the random metric I chose that we want to minimize over time, say that this somehow represents the performance of this system. And we have these constraints. So our inputs u have to be between -1 and 1. And we also have what we call a state constraint. So this requires that our state has to be here between -3 and 3. So the input can't do whatever it wants. It can't move the system out of this range. Now, I did not look at feasibility issues with this when I designed this. I just said, okay, let's just say this is what I want. And that doesn't mean that if I just throw this up on the slides that this is necessarily possible to do. So that's going to that question that I mentioned earlier, that as control designers, we can't just throw any optimization problem that we want and say, okay, the process had better meet that. Processes have dynamics, and depending on the system, they may or may not be able to do the things that we just tell them, go do this. So you actually have to be really careful when you're designing a controller that's an optimization problem, so that you're not telling it to do things that are impossible. And so we want to answer the question, what's the best trajectory for our inputs if we start the system at x of 0 is 2? So now we're going to start breaking down those things that I talked about, receding horizon and other things. So one complication you might start thinking of when you see this actual example is, wait a minute, we need to implement inputs on our system somehow continuously, because if our valve is open, for example, something's coming out of that valve or nothing's coming out of that valve. We can't just have like a neutral position, like the valve is in neutral and therefore, like, what would that even mean? Physically, either something is coming out or nothing's coming out. So this means that if we were to continuously figure out what's the thing that the valve should be doing, we'd have to be constantly solving our optimization problem. But computers can't just solve instantaneously. So what do we do about this? So one way that we can handle this is by implementing our inputs in the sample and hold fashion. So that's the one where they're piecewise constant. And so the idea is we'll compute new values of u, but not all the time. We'll do them at every sampling period. So we'll compute a value of u and then we'll hold it constant. And that allows us to not have to be continuously solving this optimization problem instantaneously. It gives us a little bit of buffer time to say, okay, we solve and we can wait. Or in a more advanced way of thinking about MPC, you could start looking at what would be the implications of having a solve time on what actually happens. And so then here, looking at the receding horizon idea more, the optimal value of u to apply depends on what's going to happen in the future. So if I just say, okay, I'm only going to look at what's the optimal thing to apply right now, you have a short-sighted behavior. And so one way people kind of talk about this is with a driving example. So people will say when you're driving, you need to aim high in steering. So you don't just look right at the small piece of road ahead of you to make your decision about how to change the steering wheel. Instead, you look far and then you change the steering wheel based on what you think is going to happen. But things might not even turn out like what you expect. Someone could drive right in front of you, or some type of, maybe some animal walks out on the road. Unexpected things can happen that cause you to update your action of your wheel, but that doesn't mean that you don't try to predict. And so same principle here, you try to predict even though you know you're going to have to update. And but you can't include an infinite amount of time into the future. So the solution to this is that you want to predict what's going to happen for just n sampling periods into the future. So you're going to predict a future value of your input at every sampling period in the prediction horizon, but you're only going to apply one of these to your process. And so then the other thing is, wait, if I need to minimize this objective function over time, I really need to minimize the integral of this objective function. And then what does that mean? Because that involves future values of my state that I can't measure and that I don't know what they'll really be. So that means that I need to use my dynamic model to make predictions of X across my prediction horizon. And a similar issue with my constraints, I need to say, if I'm going to require a constraint to hold at all times, I need to make predictions of the state in order to actually enforce this type of thing. So we need to numerically integrate our process model. There are different ways of handling that. I'm going to present just like one idea that I think demonstrates the concept of how a process model is related to constraints, but there's other ways of writing these things. And so this is a case, let's just say I have n is 2. So my prediction horizon is 2. I have 2 sampling periods in my prediction horizon. In each sampling period, let's just say, super simple case, I have 2 integration steps. Now, this is probably not like anything you would really do, but this at least demonstrates how you can go from an MPC, like written in the nice math form that we have, into something that can actually be solved as an optimization problem. So here we need to say, okay, let's use the explicit Euler numerical integration method and say X at the next time is equal to X at the original time plus my integration step times the right-hand side of my differential equation evaluated at the current time. And I can write this for all the different integration steps and end up with these equations. I can also numerically integrate my objective function by saying I'll take these small intervals that have this length of a time integration step and then multiply those by what was in the integral. And so I can also then discretize my state constraint and say I'm going to enforce it on all the different time points that I'm simulating. So with that, I now end up with a set of decision variables that are these 6, and I have all of these constraints from what I just wrote. And so now I can write my original MPC as this optimization problem that we can actually start thinking about coding now. So here, my objective function no longer just looks like this symbolic integral. I've actually translated it into something that I can put in a computer. And then same thing with all of my constraints. I don't just have a process model there anymore. Instead, I've made it so that my process model is now incorporated in the constraints in the objective function, and I've got something I can solve. And we still have this thing here, X of T0. So at the initial time, that's equal to 2. But at the subsequent times, it's the measurement of the state. So as we said in our control loops, we have a sensor. The sensor makes a measurement and communicates that measurement to the controller. And the controller then uses that to compute the inputs. So here, the measurement is this X of T0. And so now we're going to look at a very simple, that simple case in the Google Colab. And so I'm going to choose this integration step of 0.01. This is for demonstration only. In general, you have to do a good look at your dynamics and you have to see if you're using a small enough integration step and things like this. I'm just doing this for demonstration of being able to show how you can put an MPC that's coded in a very in like a very clear way that we can write on paper with almost like only a few constraints, how you could translate that into something in an optimization problem. But I'm not saying this is necessarily a good integration step. I have not checked that for this. This is just for demonstration. We said our sampling period is going to be 0.02, and I'm going to run this for 2 sampling periods because it becomes infeasible after that point. So people probably should be more careful when designing the MPC. And that's just a part of, again, of MPC design, is being careful when you set up your original problem, so that from both the perspective of the physics and the way that the mathematics and the optimization have to play together, that you don't end up with a situation where you have problems that can't be solved and that you're trying to control your process with something that has no solution. So here I'm doing the same thing as before. I'm bringing back the solvers into this Google Colab document. And I'll then after that one, now my code is a little longer. So in this case, I need to define my integration steps, my sampling periods, my number of sampling periods, which I said I was going to use 2. And then what we have here is that we're going to need to set up our dynamic model we're going to set up our optimization model, so our Piomo model here, every sampling time. So at every sampling time, we need to solve the optimization problem again, because we have a different state measurement, and therefore we actually have a different optimization problem. And so here you can see we do the same thing as before. We actually have 6 decision variables here, as we just said. We can set all of their bounds. Then we have our objective function, and we have all of our constraints, and then we're going to solve with IPOpt. Then we're going to take the input that we get, and we're going to apply it to the process. So this part here represents the actual system. So the system is such that the input is being computed by our optimization problem. And then we can see how the system evolves with time in this case. So I just solved it. Here's the output of IPOpt for those 2 sampling periods. It says in each case that it was able to solve. And then here, I'm going to plot the results. So here's what we get. So we can see that our state was increasing over time. And here the inputs, I printed them out down here. They were basically approximately 1 the entire time. So if you look back at our constraints here, that's the upper bound of our inputs. So in both cases, the one that got applied to the process was about 1, even though it looks like this step, which does reflect piecewise constantness and sample and hold, but really like the number of significant figures, oh my goodness, it's approximately just at the upper bound, it's approximately 1. But then that shows you the idea of how an MPC works, and that optimal control actions were computed for this process, at least optimal according to the way that I set up the optimization problem. And I think the interesting thing about the infeasibility and things like that I'm talking about is that that doesn't mean I set up my optimization problem right. So just because I could write it as a control law, as you can see from this discussion, there's a lot more that goes into understanding MPC and really making good ones than just, oh, great, I understand optimization and I've got a controller there. You have to actually make sure that your MPCs are workable, that they're tractable, that they have a long enough prediction horizon, and all of these different things that we didn't cover here. But at least that gives you some basic idea of the major principles of MPC. Any questions? All right, not seeing any. I'm going to keep going here. So with that, I now have given enough background that I can start giving some sense of where the research is in my group, which we focus on model predictive control and trying to advance the field of control through looking at these really intelligent control laws. And so their intelligence is really a lot of the reason we look at these, because as you can kind of see, the progression of this discussion went from saying, okay, I can kind of do this more ad hoc tuning, which you could use optimization and stuff to try to get better tuning than what I did earlier, where I just tried different tunings of my PI controller until it looked a certain way, and I said, okay, I'm good with that. But in the end, that was like PID, you're stuck with a certain form. Then we moved on and said, well, what about model-based control? And in the end, then it was still good, but it didn't have a way of accounting for constraints and performance like optimal solutions in a very explicit way. And so then MPC does have that ability to account for all of these things and be a more intelligent control law design. And so that's the reason that we find a lot of interest in that from the perspective of research and pursuing what could be done in this field. What are the possibilities? And so what we look at from a next generation manufacturing perspective then is trying to say, okay, how does intelligent control allow us to try to do new things that will help us make more money, help us operate more safely, and solve other current problems? And so, for example, the idea of next generation or smart manufacturing is that we want to operate processes profitably, autonomously, safely, securely. And control can play a big role in that. So one way that we can start looking at profitability, for example, and how can we advance control to enhance profitability? Well, the current state of the art, that the way MPC is typically used in the chemical process industries today, is according to this figure. So a steady state economic optimization problem is solved, called real-time optimization. This one determines the economically optimal steady state. And it sends that to a tracking MPC. So that's an MPC with a quadratic objective function. And that MPC will then try to compute control actions that drive the process state to the steady state that was told to it. And so this is great because the MPC is helping the process to operate at an economically optimal steady state, even when there's disturbances, and it's able to kind of optimize the trajectories back to the steady state in some sense if the process state is driven off of those trajectories. But it doesn't really allow the MPC the flexibility to explicitly optimize economics itself. It's still a little bit limiting. And so that motivated a lot of research that's been going on for around the last decade, in what we call economic model predictive control, or EMPC. And so this is really a generalization of MPC, where it allows your objective function of your MPC to be anything. So unlike how in industry today, typically your objective functions for some type of continuous large-scale operation that's not batch would probably be something like this. So trying to force the system to the steady state. With economic MPC, you don't necessarily force your system to a steady state, and instead you just say, please optimize the economics controller while I'm operating. And this might be particularly useful, maybe in a case like if you have a time varying objective function or constraints. And you might say, when would I have that? Well, if your objective function, for example, is something that takes electricity prices explicitly into account, and maybe those are changing throughout the day, or other things like other types of prices, then maybe this is helpful at allowing you to not necessarily just try to track one steady state, but to sort of dynamically update what you want to do in response to your changing operating environment. And so here you can see the idea of what it might look like if something was operated dynamically. Maybe that means that, like you can see here, the system is clearly operating in a stable fashion, in the sense that it's not going crazy. None of these states is going off to infinity. I'm not getting a runaway reaction or something very problematic, but they're not operated only at a steady state. They're kind of being oscillating, and they're changing with time, but maybe for some systems, something like this might be better than just tracking steady states. And so that's the idea of economic MPC, that you develop your optimization problem so that it has an economics-based objective function, that you have some dynamic model, you measure your state, you have input and state magnitude constraints, and then you can also add other constraints. So as you saw, there's a lot of flexibility in this controller. Something that can happen if you're trying to optimize economics is that you might get really aggressive control actions. And so in order to try to prevent that, maybe you want to add constraints on your inputs for the practical reason that you don't want to wear out your valves. And so potentially there's ways you can actually adjust your optimization problem for practical purposes. Say, okay, I don't like the behavior I'm seeing from my controller. How can I add new constraints or reformulate it to force the behavior to be more like what I would like to see for whatever reasons you might have? And so something also that's really important for control is looking at safety and cybersecurity. And so this is also an area that we've been looking at a lot in my group. And so important safety considerations for autonomous systems include things like you want to prevent, if someone actually cyber attacks your control system, you want to prevent having any harm to individuals. And so you need to have ways of detecting someone attacks your control system and then mitigating the issues that can occur after that. Also, there's lots of things like that you might want to incorporate database models and model-based control without losing closed-loop stability. And so you want to make sure that you're developing sufficiently accurate models, dealing with changes in dynamics over time, handling the possibility that what if there's falsified data being used in your model development. So that's another cybersecurity issue. You might think about how cybersecurity is related to chemical process design and how cybersecurity issues should inform our process design strategies. And then also control and cyber attacks, and how we might need to think about impacts of cyber attacks potentially on something like process equipment. And so I'll talk a little bit about some of the things we've been looking at for cyber attack resilience for chemical process control. So if someone wants to cyber attack a control system, because of what we've been saying, you can see that that means they start to actually potentially get the direct ability to attack something like your actuators, your sensors, your controller code, things like this, that then directly impact a physical process, because the controller is right there at the interface between your cyber systems and your physical system. And so this could impact all kinds of things: safety, profit, production rates. And so cyber attacks on feedback controllers are something that we wanted to better understand for chemical processes. And so the direction of my group right now that we have on this is where we're trying to better understand under what conditions can we guarantee that a cyber attack would not, for example, impact safety or would not cause a problem. So we're trying to just understand this theoretically right now. We actually in my group do a lot of control theory based on the Lyapunov stability theory, and often backed up with our simulations, but we do a lot of theory because we want to understand the fundamental principles which underlie the problems that we're looking at. And so that's where we're at right now, trying to understand how do cyber attacks impact chemical processes? What can we do with controllers and combine with detection and other theoretical aspects of control to try to see what are the limits to which we can like push these systems to prevent cyber attacks or detect cyber attacks, et cetera? And how does that then fit in with the current state of the art in cybersecurity? And so those are the types of questions that we're trying to answer. But I'll talk a little bit about some work that we did a few years ago that allowed us to start to better understand what it really means from a nonlinear dynamic systems perspective for there to be cyber attacks on controllers. So cyber attacks on controllers could be problematic because what they do is they remove the relationships between state measurements and inputs that are typical. So as you know, in our control loop, when we're not cyber attacked, the sensor measurements have a very direct relationship to what the controller tells the actuator to do. And so all of this is connected. But when we have cyber attacks, we break these feedback loops at some point. So in my group so far, we've been focusing on state measurement cyber attacks. So that's the case where the sensor and the controller communication is broken. But you can also think of there being attacks on other aspects. We're trying to look more at what happens if the attacks are at this part where the actuator to process, controller to actuator type problem, which means like your inputs might be wrong, things like that. So we're trying to look at some other aspects, but what I'll be talking about today primarily focuses on these state measurement cyber attacks. And so the problem with these cyber attacks is that they can cause any input to be applied at the given state, because no longer is your state then related to the input that's being applied. You just sort of injected some random input right here. So this defies the standard notion of feedback control that we have. And so as a result, cyber attack resilience against false sensor measurements would mean that there has to be no way you could select an input which could create an unsafe operating condition. So then you might ask, well, how do we design detection strategies and controllers to try to help us achieve that goal of not being able to apply bad inputs to the process, even when there's an attack? And so that definition didn't give us a lot of help at knowing how to do this. And so in our work, when we first started looking at cybersecurity a few years ago, we did some simulation studies to try to help us understand would some initial concepts we have be helpful or not. And these actually gave us a lot better understanding of what it means for something to be cyber attack resilient and what it doesn't mean. And so I'm going to show here two different ideas for cyber attack resilient controllers that we looked at that time. And hopefully these will help everyone's intuition as well, just like they helped ours. And so the first idea we're going to look at is a controller implementation where we try to incorporate randomness. So I'll show that in just a second. The other thing is where we integrate feedback control and open loop control. That will be explained subsequently. But the overall conclusions we got from this work was that it's really important that you meet a nonlinear systems definition of cyber attack resilience to actually get cyber attack resilience. Like hoping that an attacker doesn't understand something you're doing is not really sufficient for being able to really be resilient. And we also then concluded that maybe we need to look at some directions, like how does process design or techniques which combine control and detection, how do those give us more power than just hoping that the control law alone can give us cyber attack resilience? And so I said that we would look at incorporating randomness in control laws. So you might conclude something like this. Well, so if someone wants to attack my controller by providing it a false sensor measurement, then if they know my control law, they know exactly the input I'm going to apply. So they could then sort of reverse engineer and say, okay, what input would be really problematic for them to apply and would harm the process or cause a safety issue? And then what state measurement do I need to provide to get that bad input? So that's like reverse engineering the control law. So then to us, we thought, okay, well, can I prevent them from reverse engineering my control law? Maybe I could do that if I made it so that it would be hard for them to know what control law I was actually going to implement. So for example, maybe I could randomly select a control law to use at a given sampling time. Could that make it more difficult for the cyber attacker to actually cause a safety issue for me? So before we could even look at that concept, we did have to say, okay, well, this concept of stability, I actually have to have stability when I'm operating a process normally under this random control law selection, and can I get it? And so we have something called Lyapunov-based Empc or LEMPC. This was developed in the group of Professor Christofides at UCLA. And this is a control framework that we often utilize in my group because it has really nice properties from a theoretical perspective and allows us to analyze and understand a lot of things. But we made an implementation strategy for using this Lyapunov-based EMPC. And this type of strategy was so that we would have multiple of these controllers and also another stabilizing controller that was more like the negative x squared minus x type controller. It's not based on MPC, it's just some other controller that we can have as a backup. And then what we would do is at every sampling time, we would randomly select one of these controllers, but then we would check if it would actually maintain stability. And we defined stability as whether or not it maintained the process within one of these operating regions. So for example, if it maintains it within this black circle, and then we would say, oh, okay, that's stable. So it's a different definition of stability than driving the process to the steady state, but it's still something that reflects that the process state doesn't fully go away from a known operating region. So we'd randomly select controllers, and then we'd see based on whether or not they were in certain of these stabilizing regions, we'd either neglect them or we'd keep them. And then if we couldn't find any that worked, we'd eventually just go to the backup controller. And so it turns out that this strategy can actually guarantee that you always maintain your state within a known operating region over time when you have no cyber attack. So then we were excited about that, but it turns out this actually doesn't guarantee cyber attack resilience. So let's look at this with a chemical process example. So this is a continuous stirred tank reactor with a second order exothermic irreversible reaction. And our control objective here was to say, could we operate our process in an economically optimal time varying fashion while maintaining closed loop stability, even when we get a cyber attack? And so here is the objective function that we use. This is the time integral of the production rate of our product. So it's somehow related to our economics. That's why this is an EMPC. Then we had these input constraints. So these are our two inputs, our feed flow rate or our feed concentration into our tank, and then our heat rate. And then we develop our constraints, which include some things related to Lyapunov functions, and those got developed here, and those are what give us some stability properties for our controller. And then, so here we show this outer blue region is the operating region that we want to keep our state within. And then in here are lots of other regions that are related to the different 7 control laws that were designed. And so if you look at this outer blue region, which is the one where we wanted to keep the state within there, when we operated this process under randomly choosing between all of these different controllers, it was maintained in that outer blue region over time. It looks a little crazy, like it's always changing CA and T over time. We would probably expect that if we're randomly selecting controllers, that it might not do a really smooth trajectory. But this is without a cyber attack. So now let's say, oh, okay, great. What if I'm randomly selecting controllers and I have a cyber attack? So here is a false sensor measurement that we applied in a case that we had a single economic model predictive controller, so no randomness, and then where we had this randomized implementation strategy where it was choosing between different controllers at different times. So then, of course, the randomized results did depend to some extent on the seed from our random number generator, but we saw that our randomized strategy didn't really do that much better than when we didn't have it. So what this figure shows here is it shows the straight line is our threshold on our temperature. We never wanted our temperature to go above this value. Now here we have what happens with the single LEMPC. We see that the temperature goes above this value not long after the cyber attack starts. So this is about like 0.01 hours after the cyber attack starts, a little bit more than that. And then we see here when we have the randomized strategy, we don't do that much better. It lasts like, a little bit longer before it goes over this temperature threshold, but it's not that it actually prevents the temperature from going over that threshold. And over here on this figure, you can see that for different seeds to the random number generator, there was different times before it passed the threshold. But still what this demonstrates is that fundamentally, the randomization alone is not enough to prevent the cyber attacks from being successful at causing this process to reach an unsafe situation. And so what this means is we didn't guarantee cyber attack resilience with that strategy. So then we could say, okay, when could we get cyber attack resilience? Well, you could get it if you do something like this. Say you have an open loop stable steady state. So what that means is that if I just apply my steady state input that is corresponding to a certain steady state, that then it will drive my process toward that steady state from a lot of initial conditions around that steady state. But this is not that helpful, because if I know what the input is that I want to apply, and I always apply the same one, I lose all of the benefits of feedback control. So great, maybe I can counter the cyber attacks, but if the cyber attacks only happen once in a great while, for the most part, I'm really operating my process suboptimally. And so this is also not good. So then in light of this, we said, all right, well, this looks like there's some challenges with just relying on control laws alone to guarantee that we maintain safety even when there are attacks. So maybe in accordance with a lot of what had been done in the literature, where a lot of times people look at detection strategies, we said, all right, let's try to integrate detection strategies with control and see if we're able to prove anything about the ways the detection strategies would need to be and the ways the controller would need to be. And then when we would be able to either guarantee we detect an attack if it's a problem, and then that we maintain safety if the attack isn't detected. And so we explored a number of different ideas at that point. We looked at some things where we were trying to actually probe for the cyber attacks by using different control actions than we would otherwise use to try to see if we could figure out that a cyber attack was occurring. We looked at things where we would have an attack detection strategy based on the predictions that we thought the state measurement should be and comparing that against the actual state measurement. And then we also had a detection strategy where we used multiple redundant, what are called estimators for the state, that try to estimate what the state is when they don't have all of the measurement data. We would have these redundant estimators and compare their results against each other so that they would sort of cross-check each other. And with these, we developed a variety of different like theoretical considerations to say, like, okay, under these conditions, we either can or can't prevent the cyber attack from being successful at impacting safety, or we can only prevent it from impacting safety for a short time, things like that. And so that's in many ways the frontiers of where we're at right now in our work on cybersecurity for chemical process control systems. We're looking at just these various ways to try to see what more can we do and under what conditions do we actually get cyber attack resilience. And so that's sort of an overview of where we've been at on that from a control theoretic perspective and a model predictive control perspective for nonlinear systems. And so I also wanted to mention that some of the other work in our group, we've been looking at cyber attacks impacting potentially equipment materials. And so for this, we've been doing simulations in ANSYS Workbench, where we've been looking at how if we operate a reforming tube, so this is a tube for steam methane reforming, and we have there be no cyber attack versus there's a cyber attack that increases the temperature of the outer reforming tube wall, then how does that impact things like stress and strain in our equipment? And that just gives us a better sense of the use of these high fidelity simulations in order to better understand impacts of cyber attacks on systems, or even just to understand the impacts of other advanced control strategies on systems, and allows the use of that for analyzing not only the way that the process is going to behave, but also the way that the equipment is going to behave when you have certain controllers. And so with that, I'll make some final remarks here. So the success of next generation manufacturing in many ways depends on the usability, safety, and security of advanced controllers. Optimization-based controllers are an example of a flexible automation framework that can optimize profits in real time. But there's a lot of things that are still open from both theoretical and practical perspectives to be able to better understand how they can help us meet a lot of next generation manufacturing goals. So some of the things that my group has looked at in this area have included things like looking at how we can design control constraints to update in response to different things. Like, for example, could you ever guarantee that there are certain constraints that even if they were updated in response to something as not reliable as something like a user preference, would you still be able to maintain stability? Or things like, what do you do to address cybersecurity via detection and control combinations? We've looked at things about how can controllers help us gathering data that we want to use for model identification, and how could that, what are the benefits of doing that or the limitations? What are the interactions between economic model predictive control, control system, cybersecurity, and process and equipment design? And so these are some of the things that we've been looking at, but the field of process control is really exciting. There's always so much to look at and to understand, and further advances are needed in control for better moving us toward intelligent, safe, secure, and profitable control systems that can really help with next generation manufacturing. And so I'd like to thank our funding sources for the work that was presented, which include the National Science Foundation and the Air Force Office of Scientific Research, also the Wayne State University Research Grant, Wayne State University Engineering's Research Opportunities for Engineering Undergraduates Program, Wayne State University Startup Funding. And I'd really like to thank my students. My students are amazing. And so the work that you saw presented here includes things that are done by my different PhD students, or that might have been related to work done by a master's student previously in our group, or an undergraduate student previously in our group. We have a lot of also great undergraduates working in our group right now. And so I just really want to give a great shout out to all the Wayne State students, because they are just fantastic and always go way beyond, over and above my expectations, and they do all this great work. And so with that, I'll stop here, and hopefully that gave a good idea for everyone of the way model predictive control works, how it fits in with other control strategies you could use, its flexibility, and the ways that it can impact next generation manufacturing and be useful for a lot of the questions that we have and that we want to answer. And I'm happy to take any questions. Thank you all so much for coming.
Thank you, Helen. This is great. A great talk. I think that as we normally do that, if you have any questions, please just unmute yourself. Go ahead and ask. If you are shy of to ask directly, you can also use in chat, to ask the questions.
Helen, thank you very much for your presentation. I have this is Chin Anton from Mechanical Engineering. I have two questions, if I may. We're interested in dealing with problems that have so-called time-varying systems, that systems whose coefficients in the equations are time-varying, and this time-varying coefficients depend on coupling with another system's response or behavior. How well does your the general methodology of MPC optimization that you have mentioned, how well does that apply to that kind of systems?
Yeah, so I think that if what you're doing is you're just trying, essentially, if I understand your question right, you're trying to change your dynamic model. So instead of the ones that I was presenting that didn't have time varying coefficients, you want to use ones that have time varying coefficients. As long as you can put those in your dynamic model. So in the MPC, you have to be able to predict into the future. So if you have some prediction of how those coefficients are going to be varying, so that you can actually write a dynamic model that's predictive into the future, you should still be able to incorporate it in a framework like this.
I see. Okay, yeah. So in our case, the time varying coefficients actually depend on the behavior of, it's coupled to another system basically. It forms a couple systems. So you think there is still the MPC methodology that you mentioned could still be possibly applied?
I think that so what MPC does is it actually allows you to know your process model and your constraints, and then to say, okay, if this is what's true, then what should I do? So if you know if you're able to model all of these things that you're describing, then what the MPC would do is it would just say, what's the optimal control action given all of that information? I think the challenge would come if you're not able to model everything that you're describing. Like if you're saying, oh, there's like some stuff I don't know and I'm not able to put it in a model, then maybe the MPC can't account for things it doesn't know about. But if you can put everything in there, then it's just running the optimal control action given everything you've told it about how your system will behave in the future, dynamics it's related to. I think in some ways, I don't know if this is that related, but in my PhD, what my focus was on was actually incorporating valve dynamics in the controller. So you could say maybe that's like, you could think of that almost like coupling between the valve dynamics and the actual process dynamics. But then when you incorporate that in, then now what the controller does is it selects control actions, knowing what the valves are going to do and how the process is going to respond to those ways that the valves do it. But if I remove those valve dynamics, but they exist, but I don't model them in my controller, then now the problem is now my controller is using a much less accurate process model. So the control actions it will calculate might be not as good for the system as if it knows about the valve dynamics. So that's why I say I think a lot of this depends on whether or not you actually know your model as to how good your MPC is going to do. Like the degree of plant model mismatch has a large role in whether or not the MPC does a good job or not.
Okay, all right, thank you. My second quick question is, I'm very interested in what you mentioned about the cyber attack and all those things. I suppose you also because this is also one thing I'm trying to incorporate, not cyber, but in the sense of, I suppose you have some kind of, because some of these attacks are probably global, some kind of global attacks. I suppose you have some kind of crowd communication, built into your model, something like that, incorporating some of these crowd things. Am I correct?
It's a good question. So we have a research direction that we started last year with one of the undergraduates at Wayne State, and she was looking at cryptographic or encrypted control. So that's something that has been, so some people in the literature have looked at encrypted control where they're using homomorphic encryption, which allows you to do operations on ciphertext, where what they're trying to do is they're trying to run controllers on the cloud, where what they do is they send an encrypted state measurement, and then they never decrypt the state measurement at the cloud, but then they send back the encrypted control action, and then they decrypt their control action basically at the actuator. So that has been a direction that some people have looked at in the literature, and that's something that we have started trying to look at with an undergraduate last year, but I would say that's very not well formed for us yet. So I would be very hesitant to make any statements about how would that work doing these things on the cloud. But that is the direction that we have right now that's related to cloud computing, and then cybersecurity is much more on this encryption and privacy side, but we're not very far into that. So I don't have anything more to say.
All right, that's fine, because I'm not particularly into the cyber aspect of it, but I'm working more closely in traffic management and coupling traffic management, cloud, and mechanics. I think that's very new. Very few people actually look into this kind of integration. Yeah. Okay. Anyway, thank you very much for your time.
Yeah, thank you. Yeah, thank you.
Helen, when I heard the last part of your talk, I feel like wow, this is great. I wish we have more computer science security faculty can be here. So particularly when you mention homographic encryption kind of way, this has been I have a student, we recently published a paper on that, exactly we're doing some function on the vehicle. So it's similar what you said. Instead of give the raw data, you encrypt the raw data, but then you doing this process against this encrypted data so that they don't review anything. And then after they come back, you have another one, decrypted. Yeah, this is a very hot topic in the computer security these days. So I think that when you apply this to the process on the cyber attack, this is great. You already talked to John Ho a couple of times, right? I think I introduced you, but this is definitely something, cyber attack on the cyber infrastructure. This right now is a hot topic. You see a lot of potential risks here. That's great. Yeah, maybe we should, offline continuously talk about this.
Yeah.
This is good. I believe Alan left a question here that, can you see it?
Yeah, I can. So Alan, do you mean you're wondering how did Iran deal with the Stuxnet attack?
Yes.
So when you say how did they deal with it, do you mean what were their control systems that got attacked, or is that kind of the idea? Or you mean what did they do after people found out about it, and how have they changed their control systems since then? Is that more the question? Countermeasures. So I don't know what they've done since that attack happened. That attack was successful in actually impacting the centrifuges. So I guess I would say that that attack actually made an impact on the physical system. And so since then, what has been done? I would assume that control vendors have probably tried finding more vulnerabilities in their software. I would assume that there's probably more measures that people have tried to say, okay, no flash drives, and trying to just be generally more careful. But I guess I don't really know more about the explicit things that maybe those facilities might have implemented since then. So I think certainly in industry, it's a topic is like how do you make sure that your control systems are as secure as possible? And so certainly things then like software patching, or how do you apply the right types of currently known cybersecurity measures in good practice. Those would definitely be things that are of interest. I think that's what you're asking. So certainly industry is concerned, especially like chemical process industry. Certainly they have concern over cybersecurity, and they employ a lot of measures to try to deal with that by trying to make sure they have the up-to-date types of security protocols and things like that. And I think that of course probably varies by the level of resources that a given company has, because there can be anything from something as large as something like Dow or BASF all the way down to something much like a much smaller manufacturing facility. And so I would imagine that the level at which people are able to actually implement all the best cybersecurity practices probably depends to some extent on the legacy of the equipment, like how their equipment is outdated or not outdated, and then also the extent of the resources that they have. But certainly industry, the chemical process industries are quite aware that cybersecurity is a concern, but whether or not people always take action, I mean, I think that to some extent depends. I think you could even say it's very interesting that things like earlier this year, there was an attack through like a remote desktop on a water treatment facility in Florida, where someone was able to remote in and try to change the concentration of sodium hydroxide in the set point for the sodium hydroxide content to a much higher value than it should have been, which seems to suggest that maybe this person was trying to cause problems in the water supply. But then someone caught it because they were really lucky. The operator was looking at the screen right at the time and saw the person do this. But then I think that kind of is an example of like, are cyber attacks getting through? Yes. So do people care about this? Yes. Thank you very much, Alan. I really appreciate your comments and questions.
Helen.
Hi, Kasheng.
Yeah, this question from EC department. It's really a great talk. I'm interested in, when you talk about the chemical process, we have model, we have the plan model. So normally, how good are those models? I believe they are validated, right? Are they like, in the power system, we have also a lot of models. And normally, the utility and power system company, they don't want us to mess up with the real system.
Oh, yeah.
So the actual model are pretty, I would say, to some extent, pretty good. But for chemical process, are those models also fairly good, or
That's a really good question. So I would say that what I would say is, so at least in the literature, so I think you're talking about, are the ones I use good? I'm sure that the ones that I use in industry when they actually have MPCs are sufficient for doing a good job with what they need. But then in terms of like our research actually really is in many ways much more control theoretic. I'm not really modeling. I mean, I know how to do modeling, but I'm not really, modeling is not my research focus. So in general, when we have an example, if I use something like this continuous stirred tank reactor, I mean, how accurate is that? Oh, wow. That really depends, right? Because there's so many things that can happen. I mean, there's a ton of assumptions behind the continuous stirred tank reactor model. There's things like perfect stirring. There's the assumption that you actually know your reaction rate law. There's all these different things. So the ones that I was putting there are just some that kind of simulation like grade, I would say, like they don't even represent anything. Like they don't represent any particular process in particular. Now you can go through a modeling exercise where you can read the literature and say, okay, so-and-so reports the reaction rate law for this process at so much. And then you can say, okay, maybe I'm going to assume there's no reactor channeling, or I'm going to assume there is channeling, and you can account for all of these phenomena in different ways. But for what we do, where we're really looking in general at control theory, that's not, it's not so important that our models are the best model ever to demonstrate how the theory would act, and for us to understand the basic principles of like, okay, would this work? Would this not work? Under what conditions? And so I don't usually operate with models at the level of like super fidelity. Now, the things that are better are our computational fluid dynamics simulations. Those were actually basing those off of a paper where those people had validated their model against industry, and so we're trying to replicate their work by like following what they stated, but I don't have any industry data to compare against. So like, can I say that mine is necessarily accurate? I mean, I can only compare against theirs and say it looks kind of similar. But yeah, but that's not generally necessary for the work that we're doing, that our model be 100% accurate. But hopefully in the future we can get some industry partners and maybe do better at that.
Thank you. Thank you. I'm particularly interested in those controller parameter tuning. Mm-hmm. Because for a real system, for example, let's say oil refinery factory, the process can be really complicated. The system can be big. So I'm not sure, for example, if we have those parameters, if we want to find an optimal, set of control parameters. Of course, if ideally, if we have an exact accurate model, we can design a good controller, right? If it's a linear system, we have a well-established method to do that. Or even if it's non-linear, if we have the exact, the model that we probably can find a good set of, parameters there. But the real system there, so I'm not sure. So from industry, do they really spend a lot of effort there in tuning the parameters
of the model?
I know for the autonomous driving, I know for people I'm talking with, like Ford, they have a group of engineers there that run all those models. They don't know exactly what's going on there, but they can run a simulation, then try to get a set of optimal control parameters. So here for the chemical process, so is that like a parameter tuning? Is also like time consuming or sometimes really challenging to do? Or, because I think if that's the case, we maybe try there's a method we can try to significantly reduce, the control parameter tuning time.
Yeah, so generally in terms of like tuning parameters, so at a chemical plant, a lot of the controllers are going to be PID. Because it is not worth the engineering time and energy to actually make a model. MPC is used when it's going to actually make you more money. And for MPC, you need a model. But even then, a lot of industrial implementations of MPC fit a data-driven model using system identification. And then they use that model. A lot of times, chemical processes are operated around a steady state because in general, we have to produce like such and such flow rate at such and such specifications, like such and such a concentration, such and such, all these things. And so to operate not at a steady state has the potential of being like not on spec. And so when we're operating near the steady state, then fitting like a linear dynamic model, for example, oftentimes is sufficient for getting okay control. And but there still can be nonlinear implementations. We also have something called like a batch process, where in that case, it never has a steady state. It just, you throw some chemicals in a reactor and you kind of close it, and then they just react. And so then to control something like that, where the final state is different from the beginning state and there's not a steady state, then maybe having a process model could be more, having a more in-depth process model could be more helpful, but all this sort of depends on the process.
Yeah, I think my question would be like, it doesn't matter. It's okay. If it's a PID controller, that doesn't, that's absolutely fine. But for example, we could have other kind of control parameters in addition to the PID parameters, as you said, the flow rate or the temperature or the level of some kind of like fluid, whatever that operating parameter might be. So for the actual like the plant operators, so if they want to have to come up with a good like performance or operation of that plant, they have those certain parameters to set, right? So do they really need to put a lot of time to adjust those parameters, or is that not a concern?
You mean like the set points, Kaisha?
Yeah, set points or whatever that parameters might be.
So I think you should be able, if you want to do an optimization problem to figure out optimal set points if you wanted to do that. I know that optimization problems are used to determine operating steady states to operate at, and then like if that goes to an MPC, for example, then it will try to track that steady state. Does the RTO, I'm not sure if the RTO also computes set points for other controllers, but I don't see why that, like if people wanted to do that, they could definitely run like a plant-wide optimization and compute a set point. I don't know if they always do that or if they just kind of keep the set point. I don't know I don't know how it looks necessarily in industry right now in terms of changing the set points, but certainly you could run optimization to do it. Is that what you mean? Sorry.
Certainly, yeah. If they could do it, I just want to get ideas, say how long it might take or what the effort is. If it is really, if it can get it done, in a very short period of time, or it's not a big effort, or it's really a big effort, or it takes time and human resource, and to do it, then like the parameter toning could be really a topic to look at it if it is easy to do. So because when I mentioned to this, for example, for this telecommunication tower, right? We have the level of power for transmission, and also what's the angle of those antenna. So those parameters, how to set it, the people can play with it and adjust it, and it takes time. So they come up with a measure. For a reason like NSF funded project, they just use that one to adjust those parameters for them. So for example, if we have like a chemical processing facility, if there's a parameters need to be adjusted, but it takes time and effort to do it, then probably that could be an area combined with your like the control work. This parameter toning could be an interesting thing to look at it. That's just something I would like to get at, because we, some faculty at the EC and we are doing something on that.
Yeah, I think so. In terms of something like set point optimization, like optimizing the set points, to me that seems relatively straightforward. I don't see that as being like a major bottleneck in chemical engineering. I think things that more are maybe the current directions, people are looking a lot at data-driven modeling to improve the models. And then also things like how to make optimization problems faster and stuff like that. But that's really at sort of the algorithm level, like how do we do better with the optimization problems? I don't really see just like modeling the set point changes as being something that is like a big deal. I think if your optimization problem can handle it, then you just, you stick it in an optimization solver and you know the answers. But if your models aren't good enough to do that, and if your optimization problem isn't fast enough to do that, then those are more the bottlenecks. So that's what I would say, is that I think it more comes down to optimization and modeling than necessarily like that we can't find the set points. I think we can find the set points if we have good models and we have good optimization problems.
All right, thank you, Helen.
Yeah, thank you. I just thought really quick to go back to Alan, the question that you asked earlier, does the derivative element increase response time? I remember that there is a proof for what it does for like some linear systems. My gut feeling is that it's actually the other way around, but I don't remember this off the top of my head. So I'm really hesitant to give you like a firm answer, but certainly one way of seeing what it does would be to just simulate and see. But I'd have to look at a textbook to remind myself which way it goes when you have like a certain class of systems, like a linear system. So sorry that I didn't have a better answer for you on that one. Okay, yeah, does it affect it? Yeah, so the derivative element, definitely it will change the closed loop dynamics. So what happens is any control that you put in there actually changes the dynamics of the entire system. And then so every change that you make to the system's dynamics via changes in your control law, then overall will impact your entire closed loop dynamics. And so certainly changes to your control law will impact things like the response time or other aspects of dynamics. Are there any other questions? Well, thank you everyone so much for coming. I really appreciate you taking your time. I guess people can go if they want, and if someone did have a question and wanted to hang out, they're welcome to stay. But other than that, I guess people can go.
Thank you.
Thank you. Thanks very much. Not seeing any further questions, I will close the thing here. See everyone later.